Professor Sui, dear professor and the students. We are very glad that today we have two very young scientists visiting our university and our department from Seoul National University. So welcome. I yourself. That's the only Korean I know. Otherwise, so keep up. Okay, I will briefly introduce today's speaker for you. The first speaker, Dr. Jeong. He received his bachelor degree, master degree, and PhD degree from Seoul National University in 1999, 2001, and 2005, respectively. And he's now a postdoc researcher in Seoul National University. His research topic is large-scale climate variability and its impact on the atmosphere land interactions. And Dr. Kim, sitting over here, he got his bachelor, master, and doctoral degree from Seoul National University in the year 2000, 2002, and 2006. And he's now also a postdoc researcher in Seoul National University. His research topic is large-scale dynamics of low-frequency variability and data assimilation. So they are very young, about your age, okay? So I invite everybody to ask the questions at the end of the speech, okay? So let's welcome them.
Hello everyone, I'm Jee-Hoon Jeong. Thank you for thank you for Dr. Sui. Today my topic is impact of realistic land surface conditions on climate forecast of Chem3 using GSW portions. I'm Jee-Hoon Jeong, and Dr. Sui kindly invited me, and Dr. Kim, and thank you very much. Actually, I have been visited Taiwan in 2002. And at the time, it was somewhat very hot. But now the weather is very fine, so I really enjoyed the time here. So anyway, I forgot. 新年快乐. Let me talk about my talk. This is the introduction. So synoptic weather forecasts are mostly dependent on initial conditions of atmospheres, well known. It's a kind of indirect problem. But in extended to serial forecast, it's highly dependent on the slow valley boundary portions, such as SSTs and TICs and SF conditions. It's a kind of boundary valley problem. And other low frequency variabilities in atmosphere can have the forecast, such as MJO and broking. But the influence of SST is mainly confined to narrow tropical latitudes, and atmospheric variabilities are still not sufficiently understood and resolved by climate model. This figure shows the relative contribution to precipitation variance in GCM simulated in NASA model. So you can see the variance explained by SSTs are confined to tropical latitudes. In most of the extratropics and subtropics, the chaotic atmospheres dominate the signal. But the chaotic atmosphere part is nearly unpredictable in GCMs. But in most of the continental region, there are high contribution due to the land surface and atmosphere feedback processes this way. So this is my key motivation in this research. Due to their longer memory than atmosphere, I think 1 to 2 months, slowly varying land surface conditions such as especially soil moisture and the subsurface temperature are believed to provide additional predictability to seasonal forecast. So accurate initial and land surface conditions are essential for extended to seasonal prediction. This is a sample of promising result by Costa and Meyer. The Costa tried successfully predict the drought in 1988 in US with the initialized Landsat condition, successfully predict the drought condition. The Meyer tested the global influence of the initialized soil moisture, and the significant error in precipitation and temperature prediction is reduced significantly. So in this research, I also try to initialize global Landsat conditions using the Landsat model and atmospheric observations. And I also investigated its impact on seasonal forecast in a series of Landsat GCM experiments. But there is a big difficulties in Landsat initialization. It's mostly due to the lack of observations in Landsat point. This is a sample of the global soil moisture data bank. There are only few stations of China and old Soviet Union. There are some stational observation of the soil moisture is available, but its spatial and temporal sampling is not so sufficient to initialize the global model. And another way is by remote sensing by satellite, but it enables the coverage of the global Earth surface, but it's only applicable for the thin upper soil layer. It's I think it's just 1 and 2 centimeter. It's just where the atmospheric signal is dominant in a fast adjustment timescale. So it's useless to help the seasonal forecast. So alternative Landsat initialization technique is used using Landsat model. As you know, the atmospheric observation is more abundant and accurate than the Landsat observations. So driven by relatively this atmospheric pushing, drive the Landsat model in offline mode and try to estimate the global Landsat fluxes and state variables such as temperature and soil moisture and hydrological quantities. But so in this research, I used the observed pushing from GSWP project. The GSWP is a kind of it's a comparison project of the Landsat model by offline simulation of the multiple Landsat model using externally specified atmospheric pushings. So various global observations are included in the GSWP2 pushings, such as temperature of CRU and the SRV radiation data and the GPC precipitations. And these observations are hybridized with the model-based asset neural sheet product to resolve the higher frequency temporal variation. So the GSWP provides 1:1 spatial resolution and 3-hourly temporal resolution data for 1983 to 1995. But if the Landsat model is perfect, and even though Landsat model is perfect, and the pushing data is perfect, suppose, but still we have a problem to use the Landsat estimate to climate simulation. That is due to the climate drift and initial shock problem of due to the bias between the observation and GCM. This is a schematic diagram to explain. So the solid line represents the atmosphere simulated in GCM, and this is observed atmosphere. as you know, there are huge differences between the GCM's climate and the observed atmosphere. Not along the bias. Also, there are huge differences in variance. The dashed line is kind of length of variables. It follows the overlying atmospheres, and this is length of model caused by observation. Then, if the length of variables by the length of model estimation is used for climate simulation in GCM, then it leads to the huge difference, the huge bias leads to a climate triple. In time scale less than a week, the length of condition follow abruptly moves to model world. This is one sample. So Domeyer tried to initialize the one point. This is an initialized point of soil moisture. This is the observed world, and the model quickly drifts toward the model world. So this program makes the seasonal forecast useless. So we should overcome this problem. So Gaussian data should be adjusted based on the model's own characteristics. So bias elimination is bias, and amplitude scaling are needed. This is a sample of the mean bias of the model are used and the observations. There are huge differences between the model and observations. And the model shows the model's variance is weaker than observations. I correct the observation data based on these formulations. Firstly, based on the monthly climatology of CAM3, and I added the monthly anomalies of GSWP Forsching's observation scaled by the variance ratio between models and observations. And for higher frequency variability, I added the diurnal to synoptic scale variabilities in here. So for wind and temperature and humidity, I use this formulation. But the precipitation and radiation is discrete variables. It's impossible to apply this formulation. So in these two variables, I just normalize. I just correct the amplitude by these formulations. The 3-hourly observation is corrected by the ratio between the monthly means between the model and observations. This is the result of the correction of the Forsching. Left figure is original one. There are huge bias in Forschings, but it's almost eliminated by this process. Now I have now the experiment to investigate its impact, the initial conditions impact on seasonal forecast is verified using this series of experiments. The LG simulation is offline calculation of GM3 versus model. It's caused by adjusted GSWP Forschings and calculating the initial length of conditions for AGCMs. So this L means length of model and G means GSWP. And in the red 2 experiment is AGCM simulations. The ALO is a control simulation of CAM3. It's AGCM. It's a any type integration with the observed SST for this period. with 10-member ensembles. The A means AGCM, L means research model, and O means observed oceans. And the final experiment is with the research initialization experiment of Chem 3. So G means research conditions. So 1 month forecast with initial research conditions from LG, and atmospheric initial conditions derived from ALO is performed for May to September for 1983 to 1995 with 10-member ensembles and observed SST. So there are the difference between these two experiments is only the initialized research conditions. So next, I'm to impact evaluations. I first investigate the signal to noise ratio. The signal is the external variance, and the noise means the internal variance. That means the signal part is variance by ensemble means driven by external forcings. That means if the research conditions act as boundary conditions, the signal part will be large. But the noisy part is variance of difference between the ensemble members. So it's just means the chaotic atmosphere. So if the signal to noise ratio is larger than 1, then the experiment is the atmospheric anomalies are really caused by the research conditions we can think. This is the result. This is the result of ALGO and for precipitations and substrate temperatures. The blue color is over 1. Signal to noise ratio is over 1 region. It's in over tropical latitudes and some subtropics and several regions of extropics. There are the high signal to noise ratio is shown. This is the difference between the ALGO minus ALO. That means the impact of land initializations. We can see over middle of Africa, in Asia, and middle of North America, and northern South America. We can see the high impact of the large impact of the research initializations. In substrate temperatures, the impact is more strong. You can see over Eurasian continent, and now in Australia, and more stronger signal over here. That means the research conditions really act as a strong boundary pushings to make large variance in ensemble means. Next evaluation is R-square statistics by Costa et al. This statistics means the potential predictability within the system by the research initializations. Assuming the one ensemble member in each forecast has one correct realization of nature, and the average of the remaining 9 ensembles as a forecast, and then we have 65 pairs of nature and forecast pair because we have 5 months in each year and for 13 years. So we can calculate the scale of correlation coefficient, and I repeated this process with our ensemble members and make the average. Then the average R scale represents the model's potential predictability. The higher potential predictability means the higher consistence between the ensemble members. This is a schematic picture diagram. Each circle means each ensemble members. If the R scale value is high, then the the consistency between the ensemble members was high. But if the rho value of R superior means there are no consistency between the ensemble members. That means the potential predictability means also means whether the Lensup's condition really acts to make a consistent anomalies or not. So this is a result in precipitations.
Can I ask you a question?
Yes.
In your calculation R square, what is the correlation? Is that in among different samples, in space or temporal correlation?
Yes.
Yeah, you mean the square of correlation coefficient?
Yes.
What is the correlation coefficient?
Yes, we have 65 the pair.
What is 65?
So I performed the ensemble forecast from May to September each year for 5 months.
For 5 months.
Yes, and I performed from 1983 to 1995. So we have 65 cases.
So you're using monthly data.
Yes.
So this is temporal correlation at each grid point.
Yes.
Thank you.
This is a result. The upper panel is a result of with length initializations. The high potential predictability is found in tropical latitudes. Here. This is without length initialization. So similar. This is a difference between the two. You can find the impact of length conditions here. High values observed here. This is a subset temperature case. It's much better than precipitation. This is difference. There are many regions shows the enhancement of potential predictability due to the length conditions. Large regions. This result shows the high seasonal and regional dependency. As you know, the memory of land surface condition is highly dependent on the precipitation and radiation, which controls the soil moisture evaporation relationship. So, and the precipitation and radiation show strong seasonality and regional differences, so as does the impact of land surface initializations. This is R-scale result for each month. This is for precipitation and temperature. This is idealized case. You can see in Australia, the impact of the initial land surface condition is weak in May, but it gradually increase and maximize in July and decrease. In summer, in Australia, in southern hemisphere, it's winter, so radiation is weak in summer. So I think this is because of radiation. If the radiation is too strong, then the soil moisture is quickly evaporate. So the memory of the land surface is very low. In precipitation case, we can see the influence of the monsoon. The signal is a little bit weak, but in May we can find the enhancement of predictability in East Asia, but it decreased in June and July. I think it is because of the large precipitation in this period, and it's a little bit increase in August and September. If the land surface condition is well initialized in first day of the simulation, if there are large precipitation occurs, then the memory of the lens of condition is quickly removed. So I think this is because of the seasonality of the precipitations. And another thing is we can see is regional dependency. This is the impact of lens initialization in R-square values. This is the Japan's climate classifications. You can see this figure and this figure. There are the impact of lens condition is mostly concentrated in some special regions, like the pink and red regions in this region. I think this is the strong. This region is mostly the equatorial region and kind of arid, semi-arid region. It's over transition zones, kind of transition zones between the humid and dry areas. So also in temperature forecast simulations, we can see the similar region of relatively dry regions. We can find the large increase of the potential predictabilities. I'm sorry. Actually, I made this half of this figure in here, so I didn't have much time to interpret. So, sorry, but this is my summary. The initial value of the lens of conditions are estimated from offline calculation of LSM, and it's a climate drift and initial shock problems in the ensemble simulations were eliminated by renormalization. It's a correction of Cauchy data. The results of ensemble experiment shows potential improvement of climate simulation by realistically initialized lens of conditions, I think. So I think I have made a kind of bad presentations, but I think I made a lot of figures using this data, ensemble experiment data. I think the lens of conditions, the impact is very big, kind of big. So in my experiment, I didn't use the atmospheric initial conditions realistically. So I think this is my personal opinion that I think in monthly simulation, monthly to 1 month to 2 month simulation, so I think the lens of condition is more important than the atmospheric initial conditions. So I think actually I have lots of research, but I think I don't have enough time because we have 2 speakers. Thank you.
I think Dr. Jeong is going to stay here until tomorrow, Wednesday. You're leaving Thursday, right?
Yes.
So if you are interested, you can just talk to him either today or tomorrow. So before we go to the next talk, maybe we have some discussion. Do you have any questions? Any question or whatever? You can ask in Chinese. Yes.
Do you have any sensitivity study on the land survey model that
Yes.
is offline version by using the open data without any adjustment?
Yes, actually, I have tried that, but I don't have a figure. But this is only the lens of calculations. This is with the original data set of GSWP, and this is with corrected values. But the kind of difference in subsurface variables are two huge. It's very big. This is the original, this is adjusted. So I have tested just 1 year, but the result is so different. So it's a kind of useless in this case.
Do you expect the land surface models will perform at, different seasonal or regional dependency?
Yes.
Stuff?
Yes.
Do you expect that?
Sorry, pardon? What?
I mean, does the land surface model present some regional dependency?
Yes, yes.
And also seasonal dependency?
Yes. Yes. Actually, I performed for winter time. But in winter time, there are another variables, the snow. It's very, very difficult to treat the snow. It's the seasonal dependency is more heavier in snow case than in winter case. So I think.
I have another question. So my next question is, do you need to advance the biocorrection
Yes.
every time when you do the climate simulation on
Bias correction, yes.
every time when you do the
Yes. But it doesn't take a long time. I just,
my question is,
yes.
the bias correction, my question is whether the bias correction will have different bets. I mean, based on the previous model result and the observation data, right?
Yes.
So when you refresh your bias correction,
Yes.
do you need to use a new data base or you use a previous one? Say your
I just use previous one.
So you have a training period.
Yes.
Another question? I have a question. Can you go to your last chapter before your summary? Yes, this one. So this is the figures you try to discuss impact
Yes.
of land initialization.
Yes.
So for example, for precipitation,
Yes.
so you have the two experiments. The one ALO experiment is the one you have interactive land atmosphere, but with no initialization.
Yes.
And SST is prescribed,
Right.
so it's like aiming type. But ALGO is the one you have the land initialization.
Yes.
So suppose the land data is better,
Yes.
right? And then the difference in R squared here shows the regions that the land initialization has a larger impact,
Yes.
right? So how about let's focus on the Asian.
Asia.
Yeah. So for example, in China and or Eurasia, how do you think like the Mongolian grassland or those areas sensitive to the land data initialization? Does that show up in your figure? Is that the red area? Is that the Mongolian, I mean precipitation?
You mean here?
The upper
Precipitation?
Does that include the Mongolian grassland?
Yes. I think.
Is that the kind of climate sensitive area?
As you know, there are the annual precipitation is very small.
Right.
Right.
So,
So
but is this for the warm season?
yes, just one warm season.
Warm season.
Yes.
So how about the precipitation in that region in the warm season?
Warm
The
season.
variance of rainfall to the total rainfall. But how much is that in the red area?
This area.
Yeah.
Actually, the R-scale value is the exact try to explain the exact percentage of the variance.
Right.
It's kind of 5 to 10. 10%. Actually, but it's better to show this one. This one is the several focused area to calculate the R-square values.
Okay.
You can see this is ALGO and this is LO. The R-square is increased in ALGO. I also drew about the Mongolia. This is a testing. But the value is too high, too small.
Too small.
Too small. So I think I neglect that reason.
So, but from what you have obtained,
Yeah.
so you suggest if we include the better land data unitization,
Yes.
we may improve the 1 month prediction
Yes.
in that region.
Yes. Actually, I think in this region, it's very dry region.
Right. Including Tibet, right?
Yes, dry region. And I think that the soil moisture is not so effective of this region. I think just the initial surface temperature is important in this region, I think.
Surface temperature.
Yes, because in this area, the anomaly of surface temperature is prolonged. For I think about more than 1 month. So just if I just correctly initialize the surface temperature of that region, that means
So that makes sense
Yes.
because that region actually is quite different from the other region, the
Yes.
other sensitive region. Other sensitive region are in the tropics,
yes,
but in Eurasian, the red area actually indicates maybe the ice processes over land are very
Yes.
important.
yes,
But that is very difficult to do
yes.
to improve in the model. How about, yeah, I think, but how about if the other area doesn't show, like in Northern America?
North America.
Yeah.
It's actually the many prior works are focused on the North America. So there are huge increase in predictability. But I think in this model, are not so good for that area. But
Is that model dependent? You are saying?
yes, I think.
So Randy Carson used the NASA Gaudi
Yes,
model,
yes.
and this is NCA model.
Yes, this use kind of the mosaic model, but I think the Randy Costas region, there are two kinds of the resource model. One is the catchment model, and another is a mosaic model. I think that the mosaic model is more complicated and sophisticated, and catchment model is in global sense it's not so good. But the predictability sense, the catchment is shows the better result. So in this model, you can see here there are also the possibility in North America, but it varies in very much in dependent on months. So I think that the average map there are no signal.
Okay, so model dependent.
Yes.
Okay, any question? Now maybe we can go to the next talk.
Yeah.
Thank you.
Thank you.